For thousands of years, it's been one of the world's great mysteries. Just how were the pyramids built so deep in the Egyptian desert?
The desert does not lie. It has no reason to. For 4,500 years, it has held its silence, pressing its weight against a structure so extraordinary that the greatest minds of every civilization that came after it, Greek scholars, Arab astronomers, Napoleonic engineers, Victorian archaeologists, and now artificial intelligence systems processing billions of data points per second, have all stood at its base and felt the same thing. Not wonder, exactly. Something closer to unease. The Great Pyramid of Giza was completed around 2560 BCE. When it was finished, it stood approximately 146.6 meters tall, the tallest man-made structure on Earth, a title it would hold for the next 3,000 years. It was built from roughly 2.3 million stone blocks. Some of those blocks weigh as little as 2.5 tons. Some weigh as much as 80 tons. The base covers 13 acres of desert with a level of flatness so precise, a deviation of just 2.1 centimeters across the entire surface, that modern construction crews working with laser levels and GPS coordinates struggle to match it. Those numbers are not disputed. Everyone agrees on the numbers. What no one can fully agree on, what has driven Egyptologists, engineers, architects, astronomers, geologists, and a seemingly endless parade of theorists to near madness, is the how. In 2025 and into early 2026, that question erupted into public conversation with unusual force when AI systems, most prominently Grok, developed by XAI, became the center of an enormous storm of online discussion. Videos circulated claiming that when these AI systems analyzed the totality of available data surrounding the Great Pyramid, they returned conclusions that the mainstream narrative could not satisfactorily explain. The claims were dramatic. Some were irresponsible. Most were packaged inside breathless narration over AI-generated imagery, designed to generate views rather than generate understanding. But buried inside that theatrical packaging was a real intellectual tension, one that serious researchers have been sitting with for decades. And understanding what the AI actually found, as opposed to what viral content claimed it found, requires going back to the beginning. Not to 2025. Not to the 1800s when Western explorers first mapped the plateau in obsessive detail. All the way back to the west bank of the Nile, approximately 4,500 years ago, where a pharaoh named Khufu decided he wanted to live forever. Khufu was the second ruler of Egypt's fourth dynasty. He came to power around 2589 BCE. And by ancient accounts, including the fragmentary papyrus of Wadi al-Jarf, discovered as recently as 2013, he immediately set about building something that would announce his divinity to the ages. The structure that rose from the Giza plateau over the following 2 decades was not merely a tomb. It was a theological statement, an architectural argument, a declaration that the line between human and God was thinner than the horizon. It was a project of such staggering ambition that the logistics alone stagger the modern imagination. Here is the arithmetic at its most basic. Among the roughly 20,000 workers that most estimates suggest were involved, if construction truly took about 20 years, then each worker would need to be responsible for placing roughly 12 blocks per day, every single day, for 2 full decades. That sounds almost manageable, until you consider what placing a single 2.5-ton block actually involves. The quarrying, the transport, the lifting, the precision placement. And then there are the blocks that weigh not 2.5 tons, but 80. This is where the arithmetic stops feeling manageable and starts feeling like a different kind of problem entirely. When AI systems were directed to analyze the totality of what we know about the Great Pyramid, the dimensions, the tolerances, the materials, the logistics, the workforce estimates, the tool marks, the astronomical alignments, the geological surveys, the engineering analyses, they were not doing anything mystical. They were doing something that rigorous scientists do every day. They were looking for consistency. They were asking whether the inputs match the outputs, whether the cause adequately explains the effect. And in several specific areas, the answer that came back was, not entirely. It is critical to understand what this means and what it does not mean. It does not mean alien architects. It does not mean lost supernatural civilizations. What it means, what it has always meant to the serious researchers who were asking these questions long before any AI system was trained, is that we have been carrying a gap between what we know and what we assume, between the evidence and the confidence with which certain conclusions are stated, between probably and certainly. And that gap, when examined rigorously, is more interesting than any conspiracy theory. The AI analysis did not begin at the scale of the pyramid. It began at microscopic scale, with cut marks. Inside the king's chamber sits a massive red granite sarcophagus. Scattered across the Giza plateau are worked stone blocks and discarded fragments. When high-resolution 3D laser scanning is applied to these surfaces, the optical data reveals something that sits uncomfortably inside conventional explanation: tubular drill grooves and precisely linear cut lines carved deep into red granite. The conventional account holds that Egyptian craftsmen used copper tubes together with quartz sand as an abrasive. The copper tube rotated against the stone, the quartz sand ground away the granite, and with patient labor, precise cuts were achieved. The physics, however, produce a complication. Copper has a hardness rating of approximately 3.5 on the Mohs scale. Granite is not a uniform material. It is a complex crystalline matrix. Within that matrix, quartz crystals reach a hardness of 7. Feldspar, the other dominant mineral, sits lower. A soft metal tool working with abrasive sand would encounter dramatically different resistance as it moved from softer feldspar into harder quartz. Tribological analysis, the science of friction, wear, and lubrication, predicts that such a cutting edge would deflect, producing irregular and chaotic surface marks as it skipped and slipped across the hardness gradient. The laser scan data from Giza shows something different. The spiral grooves inside drill cores are parallel, consistent. The feed rate, the depth advanced per revolution, has been measured and found to be extraordinarily uniform. For a cutting edge to pass through alternating hard and soft crystal zones at a stable depth without deflecting, without slipping, without leaving the wandering signatures that Bronze Age abrasion would predict, the rotational speed and applied pressure would need to be far beyond what hand-operated tools could deliver. Now, here is where intellectual honesty demands a careful distinction. This is a genuine anomaly in the data. It is not, however, proof of advanced extraterrestrial technology. What it is proof of is that we may be underestimating the sophistication of ancient Egyptian drilling methods. A small number of researchers have proposed that the Egyptians achieved high rotational speeds through mechanical means we have not yet fully reconstructed. Others have noted that the abrasive qualities of certain Nile region sands, combined with weighted drilling, might produce more consistent results than simple tribological models predict. The anomaly is real. The explanation remains genuinely open. And that openness is not a scandal, it is science. The cut marks are a microscopic puzzle. The assembly tolerance of the Great Pyramid is a macroscopic one, and it is, if anything, more unsettling. The original outer casing of the pyramid was built from tens of thousands of Tura limestone blocks, each weighing between 10 and 15 tons. Most of this casing has been stripped away over the centuries, dismantled to build the mosques and palaces of medieval Cairo. But the sections that remain at the base of the pyramid are available for precise measurement. And what those measurements reveal was documented as far back as 1925 by surveyor J. H. Cole, whose survey found that the deviation in the length of the base sides was less than 0.1%. The joints between casing stones, as described in exacting detail by the Victorian archaeologist Flinders Petrie, had a mean thickness of approximately 0.5 millimeters. Half a millimeter. The fit is so tight that a razor blade cannot be inserted between contact surfaces. And these joints were not dry. They were cemented, which means the ancient builders were applying a bonding material to surfaces fitted with sub-millimeter precision, across stones weighing 15 tons each. Consider what this requires at scale. 4 15-ton blocks to meet with a gap measured in fractions of a millimeter. The entire contact surface of each block would need to approach something close to optical flatness. Even a deviation of 0.1 degrees at the base, when propagated through 2.3 million stacked blocks rising to a height of 146 meters, would produce catastrophic structural misalignment at the apex. The pyramid converges. It does not wander. That geometric convergence is not accidental, and it is not achievable by imprecise means. The question is not whether a gifted artisan could flatten one block to this standard after months of painstaking labor. Almost certainly, the answer is yes. The question is how that same standard was maintained consistently, without deviation, across millions of tons of stone, produced at a rate that the construction timeline demands. That question does not have a fully satisfying answer in the existing literature. Researchers have proposed standardized templates, master craftsmen working to fixed reference gauges, and organizational systems of quality control operating at industrial scale. These proposals are plausible. They are consistent with what we know of Egyptian administrative capacity. But they remain, at present, partially inferential. The AI systems analyzing this data are not gasping in wonder. They are doing arithmetic. And the arithmetic keeps producing the same quiet alarm. The explanation we have for this outcome does not yet fully account for how the outcome was achieved. Inside the pyramid, deep within its gravitational heart, sits the king's chamber. Unlike the surrounding limestone structure, this space is built entirely of red granite. The ceiling of the chamber is flat, not vaulted, not arched, formed by 9 colossal granite beams laid across an open span. Above this ceiling, stacked in a complex structural system, are 5 relieving chambers, also granite. This entire arrangement exists to redistribute the millions of tons of pressure descending from the pyramid summit, protecting the chamber below from catastrophic collapse. Each of those ceiling beams weighs between 50 and 80 tons. The largest carry roughly the static mass of a loaded freight locomotive. The granite did not come from nearby. The nearest granite quarry is at Aswan, more than 800 kilometers south of Giza. These blocks were quarried, transported overland to the Nile, floated northward on the river, and then landed at or near the Giza plateau. And then they were raised to a height of more than 60 meters and placed with the precision required to maintain a structurally sound flat ceiling. The 2013 discovery of the Wadi al-Jarf papyrus, the diary of an official named Mirror who supervised teams moving limestone from Tura to Giza, provided direct written evidence of the barge and canal system used for material transport. This is a remarkable discovery, one of the most significant in Egyptology this century, and it powerfully supports the human labor model for limestone delivery. But Mirror's diary covers limestone, not granite, and the logistics of moving 80-ton granite blocks that could not easily be loaded onto standard river barges without risking capsizing, blocks that had to be transported overland through terrain that would have tested any wooden infrastructure, remain a subject of genuine engineering uncertainty. The challenges compound at the point of lifting. To raise an 80-ton beam to 60 meters using only the materials available in the Bronze Age archaeological record, cedar wood, plant fiber rope, biological pulling force, the material science produces unpleasant numbers. A hand-braided rope of standard cross-section would fail catastrophically under the tensile stress of an 80-ton load, particularly when the jerking acceleration of hundreds of workers pulling in unison is factored into the dynamic force calculation. A rope strong enough to hold the load would need a diameter so great that no human hand could effectively grip it. The spatial problem is equally constraining. At 60 meters of elevation, inside the cramped architecture of the relieving chamber system, there is simply not enough standing area to position a labor force large enough to generate the required pulling force. The geometry defeats the solution before it begins. And then there is the placement itself. These granite beams were not dropped into position approximately. They were guided horizontally and lowered into stone sockets with tolerances that preserved the flatness of the ceiling. Any significant misalignment would concentrate structural stress in ways that would crack the stones beneath an enormous static load. Coordinating the final lowering of an 80-ton megalith into a narrow receiving socket is an operation that demands a degree of mechanical control, a braking and guidance system, that goes beyond what human muscle pulling on rope can reliably deliver. This is not a fabricated problem. This is a genuine engineering puzzle that has occupied serious researchers for decades. And it deserves to be stated clearly rather than papered over with the word, probably. The conventional explanation for how blocks were raised is the ramp. Ramps have ancient evidence behind them. Tool marks, pictorial records, and logical inference all support their use. But the specific form of the ramp, for the specific challenge of the pyramid's upper courses, has never been satisfactorily resolved. The mathematics of a straight ramp are particularly brutal. To maintain an incline gentle enough for laden sledges, approximately 8 degrees, the upper limit at which workers could realistically haul stone without being dragged backward by gravity, a straight ramp reaching the pyramid's full height would need to extend more than 1.6 kilometers into the desert. The volume of material required to build such a ramp would exceed the volume of the pyramid itself. You would, in effect, be building a second mountain in order to build the first. This is not an efficient solution. The spiral ramp, wrapping around the pyramid's exterior as it rose, solves the length problem but introduces its own catastrophic complication at the corners. An 80-ton block measuring several meters in length cannot be turned 90 degrees at a corner of a ramp clinging to the face of an increasingly steep structure. The turning radius of such a megalith does not permit the maneuver within the available space. Workers stationed on the corner would have no room to stand. The ramp edge would be under extreme lateral stress. The physics do not cooperate. A French architect named Jean-Pierre Houdin proposed in 2007 that an internal spiral ramp, running within the body of the pyramid itself, might have been used for the upper courses. This theory is genuinely compelling. It is consistent with the structure's geometry. It has been partially supported by microgravity scanning data. And it has not been disproven. But it has also not been proven. The evidence is suggestive, not conclusive. A January 2026 study proposed a further variation, that the upper courses were constructed using internal lifting mechanisms that took advantage of the pyramid's own geometry in ways that earlier ramp theories did not consider. The researcher behind this theory explicitly stated his belief that no large undiscovered chambers remain inside the pyramid's core, consistent with the latest muon tomography data, but that smaller corridors and the remnants of construction infrastructure might still be found, particularly at greater heights. This is careful, evidence-based inference from someone who has spent a career studying the building physics of ancient structures. It is the kind of work that deserves attention and that AI systems, when used appropriately, can genuinely accelerate by modeling construction scenarios, testing the physical feasibility of different ramp configurations, running structural analyses that reveal where internal stresses concentrate, and identifying where in the existing literature the evidentiary basis for widely accepted claims is thinner than the confidence with which those claims are made. The pyramid's mysteries do not stand alone. When similar analytical attention is directed at other monumental stone structures built by ancient cultures across the globe, a pattern emerges that is genuinely worthy of serious scholarly attention, even if its implications have been dramatically overstated in popular media. At Puma Punku in Bolivia, situated at nearly 4,000 meters above sea level, andesite blocks, a volcanic stone approaching granite in hardness, bear cuts of extraordinary precision. The surfaces are smooth. The edges are sharp. Complex H-shaped blocks feature internal right angles cut deep into the material, a form of geometry that creates significant stress concentration challenges during cutting and that modern machining achieves through high-pressure water cutting or diamond tooling. At Sacsayhuaman in Peru, the defensive walls are constructed from polygonal limestone and andesite blocks weighing up to 120 tons, fitted together without mortar in a system of interlocking irregular shapes. Each block has its own unique three-dimensional profile, and yet the contact surfaces between adjacent blocks are so precisely matched that no light passes through the seams. The engineering logic of polygonal masonry, fitting irregular shapes together with precision, actually has structural advantages over rectangular block construction. The interlocking geometry distributes seismic stress more effectively, which matters significantly in the earthquake-prone Andes. These sites present real engineering questions. The tools of the cultures that built them, as recovered by archaeology, do not obviously account for the precision of the finished product. The transport of the heaviest stones challenges conventional mechanical analysis. And the fact that similar patterns of precision megalithic construction appear across cultures with no documented contact is striking. What does this pattern tell us? Here is where intellectual honesty matters most. There are two broad interpretive possibilities, and they are not equally supported by evidence. The first is that some advanced technology existed in the ancient world that we have not yet identified, either developed independently by multiple cultures that were more sophisticated than we recognize, or transmitted across cultures through contact that the archaeological record has not yet documented. The second is that we are systematically underestimating the engineering ingenuity of ancient peoples, and that the combination of patient labor, accumulated craft knowledge, and organizational capacity produced results that we find implausible only because we have conditioned ourselves to think of ancient people as primitive. The second explanation is not the comfortable one. It is actually the more demanding one. It asks us to do the harder intellectual work of reconstructing, in detail, how human beings using pre-industrial technology achieve things that strain our credibility. And it points, ultimately, not to a gap in ancient capability but to a gap in our own understanding of what ancient capability was. There is a room inside the Great Pyramid that almost no one has heard of. It sits above the King's Chamber, accessible only through narrow construction gaps. In 1838, Colonel Richard Howard Weiss forced his way in and found something no one expected: graffiti. Red ochre. Hand-painted. The names of the construction gangs who built this section of the pyramid. Their marks on the hidden walls of a space that was sealed immediately after construction and not opened again for 4,000 years. One of those gang names was Friends of Khufu. Sit with that for a moment. These were people. They had identities. They had a sense of belonging to something enormous. They ate bread and beer. The workers' village discovered in 1990 near the Giza plateau included bakeries, breweries, and a settlement complete with medical facilities advanced enough that the skeletal remains show evidence of surgical amputations that were survived. These were not slaves driven to death in the desert. The slave narrative, which dominated public imagination for most of the 20th century, has been dismantled by the archaeological evidence. These were skilled workers, organized into rotating gangs, given names, given rations, given the kind of institutional care that a state invests in people whose labor it genuinely values. The Friends of Khufu pressed their hands to a wall in a room that no one would ever see. And they left their name anyway, because they knew what they had done. They knew the scale of what they had built, and they wanted something, somewhere, to record the fact that they had done it. When viral AI content suggests that the pyramids were built by beings with lost technology or extraterrestrial intelligence, it does something that should make us pause. It erases those workers. It looks at the inscription in that hidden room and says, "You were not capable of this. Someone else must have done it." The archaeological evidence says otherwise. The evidence says they were extraordinary. The Grok AI conversation that swept through online platforms was, in most of its viral iterations, theater. AI systems do not walk into museums. They do not dig sand. They do not make discoveries in the field. What they do, what all AI language models do, is process text, synthesize information across large bodies of literature, and identify patterns, inconsistencies, and gaps that would take individual human researchers years to surface manually. When an AI system is asked to analyze everything we know about the Great Pyramid, it is not doing something mystical. It is doing what any rigorous scientist would do if they had the time to read every paper, every archaeological report, every engineering analysis, every astronomical study, and every fringe academic paper that rarely gets mainstream attention. It is looking for the places where the evidence is thin, where the assumptions are load-bearing, where we have been saying probably for so long that it started to sound like certainly. That function, auditing our own certainty, is perhaps the most genuinely valuable contribution that AI can make in a field like Egyptology. Because we have been confidently wrong before. The slave narrative was taught for decades before archaeological evidence definitively disproved it. The assumption that the Egyptians could not have moved the granite without external help was stated with authority by people who had never seriously modeled the physics of large-scale stone transport across lubricated surfaces. The conviction that no large undiscovered spaces existed inside the pyramid was repeated confidently right up until muon tomography, a technique borrowed from particle physics, using cosmic ray particles that pass through solid matter, found a previously unknown void more than 30 meters long sitting above the Grand Gallery. This void was confirmed in 2017 by the Scan Pyramids project. In early 2023, a newer, narrower corridor was found near the north face. The pyramid was still surprising us. After 4,500 years, after every survey, every excavation, every theory, the stone was still holding secrets. AI did not find those secrets. Particle physics found them. But AI systems capable of synthesizing the results of muon tomography, ground-penetrating radar, 3D laser scanning, and archaeological stratigraphy, cross-referencing the physics with the historical record, can accelerate the identification of where the next discoveries are most likely to be made. That is a meaningful contribution. That is worth taking seriously. What is not worth taking seriously is the use of AI's name as a rhetorical weapon. Saying AI proved it does not make a claim true. It makes it sound authoritative while bypassing the peer review, reproducibility, and methodological transparency that distinguish science from speculation. When viral content deploys AI as a kind of oracle, it is doing the opposite of what science does. Science acknowledges uncertainty. Science follows evidence. Science changes its mind when the data demands it. The Great Pyramid of Giza was built by human beings. Egyptian human beings. Workers with names and families who ate bread and beer for breakfast and returned every evening aching to a settlement that their government maintained because their labor was valued. We know this not from inference but from the physical remains of their village, from the medical records embedded in their bones, from the administrative records left by the officials who managed their logistics, and from the red ochre inscriptions they left on walls they knew no one would see for millennia. Those workers operated under the direction of architects who understood geometry well enough to orient a 13-acre structure to the cardinal directions with sub-degree accuracy. They transported millions of tons of stone across land and water using techniques that we are still in the process of fully reconstructing. They cut granite with tools that remain, at the microscopic level, not yet fully explained by conventional abrasive theory. They fitted limestone blocks to tolerances that a modern jeweler would respect, consistently, across 2.3 million stones, while maintaining a structural convergence that rises 146 meters to a precise apex. They accomplished something so far beyond what we would predict from their material context that we have spent centuries not quite believing it. And maybe that disbelief is itself the real mystery. Not what built the pyramids, but why we keep struggling to accept that it was us. That human beings at the dawn of recorded history were already capable of something this magnificent. The pyramid is not evidence of alien intervention. It is not evidence of a lost civilization with technology that has been erased from the historical record. It is evidence of what organized human intelligence can achieve when it is pointed, with absolute focus and unlimited resources, at a single extraordinary goal. It is a monument not just to Khufu, but to the capacity of our species to refuse the limits of what is considered possible. The genuine mysteries, the microscopic cut marks in granite, the 50mm tolerances across millions of stones, the 80-ton beams lifted to 60 meters inside cramped relieving chambers, are real. They deserve continued serious investigation using every tool available: muon tomography, ground-penetrating radar, 3D reconstruction, AI-assisted analysis of the engineering literature, and old-fashioned archaeological fieldwork. They do not require supernatural explanation. They require better questions, more rigorous modeling, and the intellectual humility to say, we do not yet fully know, and that is a reason to keep looking. 4,500 years ago, workers pressed their paint-covered hands to a stone wall in a hidden room and wrote their name. Friends of Khufu. They knew that room would be sealed. They knew that in all likelihood, no one would ever read it. They wrote it anyway. That inscription is the most important thing in the Great Pyramid. More important than the King's Chamber. More important than the Grand Gallery. More important than the 30-meter void discovered by muon tomography, or the narrow corridor found near the north face in 2023, or the granite beams that strain the limits of Bronze Age engineering logic. Because it is the fingerprint of human pride. The mark of people who understood the scale of what they had accomplished and refused to let it go unrecorded, even in a room that would be sealed forever. When we ask how the pyramid was built, what we are really asking is, how far can human beings push the boundary of what is possible? The answer, apparently, is this far. And then a little further. To tolerances that should not have been achievable with rope and copper. To alignments that encode the precision of the stars. To a structure that still surprises us, still reveals new corridors, still refuses to give up all its secrets, 4.5 millennia after the last stone was placed. The AI did not reveal this. The AI helped us look more carefully at what was already there. The revelation belongs to the people who built it. The desert does not lie, but it does keep secrets, not because it is hiding them, but because stone does not speak. And we are only now developing the instruments sensitive enough to hear what it has been saying all along. The muon detectors hear it. The laser scanners hear it. The ground-penetrating radar hears it. And AI systems that